Good evening. Good evening. I am Chitabe. Our topic of presentation is Clique link-based subspace clustering. So, what is clustering? Clustering is a descriptive task that seeks to identify homogeneous group of objects based on the value of their attributes. So clustering is the task of grouping a set of objects in such a way that objects in the same group called a cluster are more similar to each other than to those in the other groups. Now, current clustering techniques can be classified in two categories. One is partitioning and another is hierarchical clustering. So what is partitional clustering? Given a set of objects and a clustering criteria, partitional clustering obtains a partition of the objects into clusters such that the objects in a cluster are more similar to each other than to objects in different clusters. The mode-seeking clustering methods identify clusters by searching of regions in the data space in which the object density is large. And hierarchical clustering is a nested sequence of partitions. Hierarchical clustering starts by placing each object in its own cluster and then merges those small clusters into larger and larger clusters until the objects are in single cluster. Now some shortcomings of PC and Kahunen-Loeb transformation. High dimensionality of a dataset is sometimes addressed by a method of dimensionality reduction, or that principal component analysis or Kahunen-Loeb transformation are used. But these techniques may reduce the dimensions, but there are two shortcomings. What are the shortcomings? The first shortcoming is the new dimensions can be difficult to interpret, making it hard to understand clusters in relation to the original data space. The second is these techniques are not effective in identifying clusters that may exist in different subspaces of the original data space. Now we have the motivations for developing new algorithms. Emerging data mining applications have special requirements on clustering techniques. The first one is effective treatment on high dimensionality. Second one is interpretability of results. Third one is scalability and usability. So, what is effective treatment of high dimensionality? An object or data record typically has dozens of attributes and the domain for each attribute can be very large. So it is not a good idea for clusters in such a high dimensional space, as average density of points anywhere in the data space is likely to be very low. Many dimensions or combination of dimensions can have noise or values that are uniformly distributed. Therefore, distance function that use the dimensions of the data may be ineffective. Several clusters may exist in different subspaces comprises of different combination of attributes. Interpretability of results. It is particularly important to have simple representations because most visualization techniques do not work well in high dimensional spaces. Scalability and usability. The clustering techniques should be fast and scale with the number of dimensions and size of input. It should be insensitive to the order in which the data records are presented. Finally, it should not presume some canonical form of the data distribution. Now we come to what is subspace clustering. Subspace clustering is an extension of traditional clustering that seeks to find clusters in different subspaces within a dataset. Now, we are interested in automatically identifying subspaces of high dimensional data space that allow better clustering of the data points than the original space. Restricting our search to only subspaces of the original space instead of using new dimensions is important because these restrictions allow much simpler comprehensive presentation of the results. Each of the original dimensions typically has a real meaning of user, while even a simple linear combination of many dimensions may be hard to interpret. Here for clustering, we use a density-based approach. A cluster is a region that has a higher density of points than its surrounding region. The problem is to automatically identify projections of the input data into a subset of attributes which with the proper with the property that these projections include regions of high density. Sorry, I had some internet issue. We were talking about subspace clustering. We use a density-based approach to clustering. A cluster is a region that has a higher density of points than its surrounding region. The problem is to automatically identify projections of the input data into a subset of the attributes with the property that these projections include regions of high density. To approximate the density of the data points, we partition the data space and find the number of points that lie inside each cell, which we call units. This is accomplished by the partitioning each dimension into the same number of equal length of intervals. This means that each unit has the same volume and therefore the number of points inside it can be used to approximate the density of the unit. Once the appropriate subspace are found, that our task is to find clusters in the corresponding projections. The clusters are unions of connected high-density units within a subspace. A data point is considered to belong to a particular subspace if the attribute values in the subspace are not missing, irrespective of the values of the rest of the attributes. This allows records with missing values to be used for clustering with more accurate result than replacing missing values with values taken from a distribution. Now we need some definitions. The first one is unit. So each unit U is the intersection of one interval from each attribute. Now selectivity. Selectivity of a unit is the fractions of total data points contained in the unit. Third one is dense. A unit is dense if selectivity of the unit is greater than tau, where the density threshold tau is an input parameter. Cluster. A cluster is a maximal set of connected dense unit. Region. A region in k dimensions is an axis parallel rectangular k dimensional set. Maximal region. A region R contained in a cluster C is said to be maximal if no proper superset of R is contained in C. Minimal description. Minimal description of a cluster is a non-redundant covering of the cluster with maximal region. That is, a minimal description of a cluster C is a set R of maximal regions such that their union equals C, but the union of any proper subset of R does not equal to C. Now we have a problem. Given a set of data points and their input parameters epsilon and tau, find clusters in all subspaces of the original data space and present a minimal description of each cluster in the form of a DNF expression. One example, in the figure 1, the two-dimensional space which consists age and salary has been partitioned by a 10 by 10 grid. One unit is the intersection of the intervals. Here an example of an unit is U is equal to age is between 30 and 35, that is 30 less equals to age less than 35, intersection 1 less equals to salary less than 2. A region is a rectangular union of units. In the figure, A and B both are regions. A is 30 less equals to age less than 30 less than 50, intersection 4 less equals to salary less than 8. And the region B is 40 less equals to age less than 60, intersection 2 less equals to salary less than 6. We assume that the dense units have been shaded. So A union B is a cluster. Now A is a maximal region contained in this cluster, but A intersection B is not a maximal region. The minimal description for this cluster is the DNF expression 30 less equals to age less than 50, intersection 4 less equals to salary less than 8, union 40 less equals to age less than 60, to intersection 2 less equals to salary less than 6. Now we come to figure 2. In figure 2, assume that tau is 20%. No two-dimensional unit is dense and there are no clusters in the original data space. If the points are projected on the salary dimension, there are three one-dimensional dense units. Two of these are connected, so there are two clusters in the one-dimensional salary subspace. The one is C dash is equal to 5 less equals to salary less than 7, and other is D dash, which is 2 less equals to salary less than 3. There is no cluster in the H subspace because there is no dense unit in that subspace. Now my classmate Amrita Ray will present the rest of the slides. Over to you, Amrita.
I am Amrita Ray. I will discuss about Clique algorithms. Clique consists of following three steps. Identification of subspace that contain clusters, identification of clusters, and generation of minimal description for clusters. Clique consists. Okay. Now we will discuss about identification of subspaces. We have downward closure property or DC property. If a cluster is satisfied in a k-dimensional space, it is also satisfied in all of its k-1 dimensional subspaces. Due to this property, identification of subspaces is carried out in an iterative bottom-up fashion. Bottom-up fashion means from lower to higher dimensional subspaces. Now, the difficulty in identifying subspaces that contain clusters lies in finding dense units in different subspaces. We use a bottom-up algorithm to find dense units that exploits the monotonicity of the clustering criteria with respect to dimensionality to find the subspace. Now we have the lemma of monotonicity. If a collection of points is in a cluster in a k-dimensional space then S is also a part of cluster in any k-1 dimensional projections of this space. Now, the bottom-up algorithm process determines one-dimensional dense unit and interaction to get two-dimensional dense unit until having k-1 dimensional dense units. We can self-join dk-1, which is the set of all k-1 dimensional dense units, to get the candidate k-dimensional unit. Also, the bottom-up algorithm discards those dense units from CK which have a k-1 dimensional projection that is not included in CK-1. Now, bottom-up algorithm can be made faster by MLD-based spanning. Now we discuss about MLD-based spanning to decide which subspaces are interesting. We apply the minimal description length principle. The basic idea underlying this principle is to encode the input data under a given model and select the encoding that minimize the code length. Now we have the determination of high coverage subspace. Determine all the subspaces that contain at least one dense unit. Then we sort these subspaces in descending order according to their coverage. That is the fraction of number of points of the original dataset they contain. Then we optimize a suitably defined minimum description length criteria function and determine a threshold under which a coverage is considered low. Then we select the subspaces with high coverage. So this was all about identification of subspaces. Now we have the process which is identifying the clusters. The input to the next step of Clique is a set of dense units D, all in the same k-dimensional space S. The output will be partition of D into D1, D2 to DQ such that all units in DT are connected and no two units UI of DI and UJ of DJ with I not equal to J are connected. Each such partition is a cluster according to our definition. Now the problem is equivalent to finding connected components in a graph defined as follows. Graph vertices correspond to dense units and there is an edge between two vertices if and only if corresponding dense unit have a common face. Units corresponding to vertices in the same connected component of graph are connected because there is a path of units that have a common face between them. Therefore, they are in the same cluster. On the other hand, units corresponding to vertices in different components cannot be connected and therefore cannot be in the same cluster. Now we use a depth first search algorithm to find the connected components of the graph. We start with some unit U in D, assign it the first cluster number and find all the units it is connected to. Then if there still are units in D that have not been yet visited, we find one and repeat the procedure. This way we find the clusters. Now we have generating minimal cluster descriptions. The input to this step consists of disjoint sets of connected k-dimensional units in the same subspace. Here, the unit to this step consists of disjoint sets of connected k-dimensional unit in the same subspace. Each set is a cluster and the goal is to generate a concise description for it. To generate a minimal description of each cluster, we would want to cover all the units comprising the cluster with the minimal number of regions, such that all regions contain only connected units. For a cluster C, in a k-dimensional subspaces, the set of regions in the same subspaces is a cover of C if every region R of that set is contained in C, and each unit in C is contained in at least one of the region in R. Now we have two methods for this algorithm. One is covering with maximal regions, and covering with maximal regions. The input to this step is a set C of connected dense units in the same k-dimensional space S. The output will be a set scripter of maximal regions such that scripter is a cover of C. We use greedy growth algorithm for this task. So, what is greedy growth algorithm? We begin with an arbitrary dense unit U1 of C and greedily grow a maximal region R1 that covers U1. Then we add R1 to scripter, where scripter is a cover of C. Then we find another unit U2 of C that is not yet covered by any of the maximal region in scripter. Then we greedily grow a maximal region R2 that covers U2. We repeat this procedure until all units in C are covered by some maximal region in scripter. To obtain a maximal region covering a dense unit U, we start with U and grow it along dimension A1, both to the left and to the right of the unit. We grow U as much as possible in both directions using connected dense units contained in C. The result is a rectangular region. We now grow this region along dimension A2, both to the left and to the right of the region. We again will use only connected dense units from C, obtaining a possibly bigger rectangular region. This procedure is repeated for all the dimensions, yielding a maximum region covering U. The order in which dimensions are considered for growing a dense unit is randomly determined. Now we have another procedure which is minimal cover. It is the last step for Clique algorithm. The last step for Clique is minimal cover. This takes as input a cover for each cluster and finds a minimal cover. Minimality is defined in terms of the number of maximal regions that required to cover the cluster. So these are all our Clique algorithms which we use. So now what we know the major steps of what are the major steps of Clique? The major partitions each subspace that is dimension 1 into the same number of equal length of intervals. Using these as basis, it partitions the n-dimensional data space into a non-overlapping rectangular units. Now, Clique's goal is to identify the dense n-dimensional units. So, Clique finds dense units of higher dimensionality by finding the dense units in the subspaces. For example, if we are dealing with three-dimensional space, Clique finds the dense unit in three related planes, that is the two-dimensional subspaces. Then it intersects the extension of the subspaces representing the dense unit to form a candidate search space in which dense units of higher dimensionality would exist. Now, each maximal set of connected dense units is considered as cluster, and using this definition, the dense units in the subspaces are examined in order to find clusters in the subspace. The information of the subspace is then used to find clusters in the n-dimensional space. Now, all the cluster boundaries are either horizontal or vertical. This is due to the nature of the rectangular grids. So these are the major steps in clique algorithms. So now we have some strength and weakness of clique. Its strength are automatically finds the subspaces of highest dimensionality such that high density clusters exist in those subspaces. It is insensitive to the order of records in input and does not presume some canonical data distribution. Scales linearly with the size of input and has good scalability as the number of dimensions in the data increases. And clique has some weakness, which is the accuracy of the clustering result may be degraded as the expense of simplicity of the method. So now in conclusion, we can say the problem of high dimensionality is often tackled by requiring the user to specify the subspace of cluster analysis. But user identification is quite error prone. Clique can find clusters embedded in high dimensional data without requiring the user to guess subspaces that might have interesting clusters. Clique is insensitive to order of input records. Some clustering algorithms are sensitive to the order of input data. Empirical evolution shows that Clique scales linearly with the size of input and has good scalability as the number of dimensions in data. Clique can accurately discover clusters embedded in lower dimensional subspace. So this is the end of our presentation. And last we so this is our end of our presentation, and thanks for listening.